Okay, so let's review. What did we do last time? Recall. Can you guys see this? Recall? Yeah, great. Um, so there was one question, by the way, that last time I think I went over a little too quickly, which was to throw at you polynomials with coefficients in finite fields. So did anyone try? This question? So the question was, is x squared plus 1 irreducible in the ring Z mod 5 adjoin x, in the polynomial ring with coefficients in the field Z mod 5. Did anyone try this? Okay, one person tried it. Dipendra, were you able to factor this? Ah, good. A bunch of you tried it. Right. So if you look at, exactly, if you look at x plus 2 times x plus 3, well, that's x squared plus 2x plus 3x, so that's 5x, plus 2 times 3 is 6. But we're working mod 5, and so mod 5, this is congruent to x squared plus 0, no x's, and 6 is 1 mod 5. And in fact, this has a root, so this factors whenever there is a solution, there exists a solution to, well, x squared plus 1 equals 0, right? If there's a root, so over the reals, there is no solution to this, so there's no root, so it doesn't factor. Over the complexes, there is. How about over Z mod 5? Well, over Z mod 5, we're asking, i.e., we're asking, does there exist an x such that x squared is congruent to negative 1 mod 5? Right? Because whether there's a root in Z mod 5 is exactly the question of whether this thing has a solution. Does that make sense? So great. So that's we know how to answer this because negative 1 is a square if and only if the prime here is. This is exactly related to when a number is the sum of two squares. Yeah, exactly. So recall, so this is exactly related to x squared plus y squared being equal to 0 mod p, which happens if and only if p is congruent to 1 mod 4, or p equals 2. Because if this has a solution in x and y, then x squared is equal to negative y squared, is congruent to negative y squared, and I can divide by y squared. I mean, y is not itself 0. I want a solution with x and y not equal to 0. And so if I divide by y, which means multiply by y conjugate, so this happens if and only if this happens, where y times y bar is 1. In other words, y bar is the inverse of y. Multiplicative inverse. Okay, so I just wanted to, so if you didn't do that homework assignment, try it. And then, so what will happen in the ring Z mod 7 instead of Z mod 5? Will this polynomial be irreducible? Right, 7 is 3 mod 4, so this polynomial will remain irreducible. There is no solution to x squared is congruent to negative 1 mod 7, because 7 is 3 mod 4, and not 1 mod 4. Okay? Can I see a thumbs up if we're kind of following this line of reasoning? And a thumbs down if you want to ask something. Okay, lots of thumbs up. Any thumbs down? Any questions? Okay, great. So we were on, what were we talking about? We were talking about rings, ideals, and Euclidean domain. Euclidean domain. This is still a review. Let's review why being a Euclidean domain implies that you're a principal ideal domain. Okay, so let's prove that theorem. So theorem, ring is Euclidean. Euclidean implies it's a principal ideal domain. Okay, do you guys remember the proof? Or a proof? Of course, there's more than one way to skin a cat. Well, what does it mean to be a principal ideal domain? Every ideal is principal. So let's start with an ideal. Exactly. Yes. Good, Yukon. So let I in the ring be an ideal. Okay? We have an element. We have this, because it's Euclidean, we have the fact that it's Euclidean comes not only with a division algorithm, but with a norm function. Bless you, Karen. And the norm function, so look at the set S, which is the set of all norms of elements, let's call them, I don't know, n, where n is in the ideal. But 0 is in the ideal and the norm function is not defined on the 0 element. So let's take out the 0 element. So far, so good? Can we clear the thumbs up so that I know if I'm losing anyone? Can you give me a thumbs down if I should review what these things are? Okay, everybody seems happy. So this is a subset of natural numbers because the norm function, remember the norm function takes an element of the ring that's not the 0 element and returns a natural number. That's what we get from being Euclidean. And so now we have a bunch of natural numbers, well, and it's a non-empty. Okay, if it's the 0 ideal, then there's nothing in here. And I is not the 0 ideal. If it's the 0 ideal, it's already principal. That's not fun. So we have this set of integers. Let little s in S be the smallest element, be least, and let D in I be an element of the ideal, a non-zero element with least norm, such that the norm of D is this smallest possible norm. So far, so good? Great. Not too abstract, or it is too abstract, but this is the third time or something that we're seeing this level of abstraction. We're starting to get used to it, I hope. Okay, so we have this element D. What do you think, if I is generated by a bunch of elements, n1 through nk, what do you think D is going to be? You want to type it in the chat? So if we want to think explicitly of I as being generated by a bunch of elements, then D will be you just have to yes, exactly, the GCD, a GCD, right? Again, it's the same argument we've kind of been using again and again and again up the wazoo. So D is this least element. Of course, D is in the ideal. So D is in the ideal. So the ideal generated by D, all multiples of D, well, that's a subset of the ideal. And what's my claim? Give me a thumbs up if you know exactly what I'm about to write, which will finish the proof that the ring R is a principal ideal domain. Kevin's writing something. My claim is that the ideal is the ideal generated by the GCD. In other words, D is equal to I. That's the claim, is that the ideal not only contains D, it contains nothing but multiples of D. Okay? Does that make sense? So how do we prove this? How do we prove this? There's a variety of ways of doing it. Kind of a very easy way is, all right, well, let's take any element. So that's my claim. Take any element of the ring. We have a division algorithm, a non-zero element. So let's divide R by D. By the division algorithm, there exist, oh gosh, I don't want to use R, because I want R for quotient and remainder. Fine, take any M in the ring. Okay? By the division algorithm, there exists a quotient and remainder, so that, let's see, which way do I want to do it? Let's say M is equal to DQ plus R, and the norm of R is I'm dividing M by D. D is not 0. Yes, less, exactly. Thank you, Karen. Less than the norm of the thing that I'm dividing by, D. Yep, less than M, where M is D in this. I've changed, the letters have switched around. Does that make sense? But that can't strictly less. Strictly less. The Euclidean algorithm says it's strictly less. But that can't possibly be the case, because D had the smallest norm of all the elements in the ideal. Sorry, I took it in the ring. I want an element of the ideal. I want an element of the ideal. Right? The way we got D was that it was the element with smallest possible norm among all of the norms in the ideal. And now I'm finding an element that's smaller than it. That can't be. But of course, the division algorithm gives us two options. Either we find something with smaller norm, or we find something with no norm at all. What's the element with no norm? So, or, yes, great, Sarah, R equals 0. Okay, does that make sense? So this can't happen. This can't happen since D has least norm. And if that's the case, then we must have that R equals 0. That implies R equals 0. That implies in this equation, M is equal to DQ. In other words, M is a multiple of D. And if M is a multiple of D, then M is in the ideal generated by D, which is just a set of all multiples of D. So what do we just show? Any element in the ideal is actually in D. That means the entire ideal is contained in the ideal generated by D, which itself is contained in the ideal, so they're equal. So that's the claim. That's the claim that they're equal. Can you give me a thumbs up if you followed that argument? Please. Awesome. Awesome. Can you give me a thumbs down, or just say, type the letter Q if you have any questions? Great. Thanks, Sarah. If any part of this didn't make sense. So this applies just as well to the ring of integers or Gaussian integers or Eisenstein integers or polynomial rings. Anything that has a division algorithm, it's automatically a principal ideal domain because it comes with a norm and it comes with a division algorithm. Pretty simple, right? Okay. Gosh, it's hard to do abstract math over the internet. Let's keep going. You guys are okay? Let's keep going. So the next thing that we did, this is still a review from back when we were all together. The next thing we did is we talked about Noetherian rings. The next claim was that if you're a principal ideal domain, then you are Noetherian. Emmy Nother's birthday was just a few days ago, maybe yesterday or something. I don't know if anybody... Noetherian. I-A-N or E-A-N? Does anybody know how to spell Noetherian? Well, I have I-A-N in my notes. I-A-N. Thanks, Kevin. Noetherian. But Euclidean is not... Euclidean is E-A-N. Anyway, all right, we'll have a spelling test later. So what does Noetherian mean? So recall, a ring R is Noetherian. This is this really weird... You can see how extremely clever she was to come up with something so weird and yet so useful. Is Noetherian if... Does anybody remember what this was about? Had something to do with ideals. Lots of people are typing. Let me give you a chance to write it in. Yes, descending ideals. Yes. Yeah. Yep. If it has the ascending idea. Okay, so if, whenever, you have a chain of ideals, I1 contained in I2, contained in I3, and so on. If you have this infinite chain of ideals, then there exists some capital N, then the chain stabilizes. At some point, the chain stops increasing. Then there exists an N such that for all N bigger than this big N, I N is equal to I big N. Okay, so let's review this one more time in the integers. So in Z, let's start with the ideal generated by 25 and 125. Can I do any better than that? And 75. What's the ideal generated by 25 and 75? So this is all multiples of 25 plus all multiples of 75. Yes, that is all multiples of 25. So that's I1. Now, what is an ideal that contains all multiples of 25? Yep, that's one. Here's another one. So we could have a couple of 25s and then maybe a 5. And then, well, we have only two choices. Either we have 5s the whole way, exactly, or as Kevin says, so we could have a bunch of 5s. And then either we switch to 1s and then we're done because this is the entire ring. This is all of Z in R equals Z. This is the entire ring. Or it's 5s all the way down. Or it's 5s forever. Okay? Yes, Sarah, exactly. Exactly. This is, well, it's a way of finding a lowest common factor when you keep adding more and more elements. If you keep adding more and more elements, if you think about the ideal generated by countably many elements, each time adding, so Sarah's question, if I have, so given, let's see, how do I want to say this? Given a bunch of elements, n1, n2, and so on, if I look at the ideal, the ideal 1 is the ideal generated by n1. Inside of that is the ideal generated I2, which is the ideal generated by n1 and n2. So of course the ideal generated by n1 is here, and now I have more things. So if you have prime elements, the ring must be Noetherian. Well, you still have prime elements in the ring z adjoin root minus 5, but that ring is not Noetherian because that ring doesn't have unique factorization. Or irreducibles. You still have irreducible elements and you still have prime elements. Why is 25 a subset of 5? Great. Okay, so thank you for that question, Alex. What does this mean? What is the ideal generated by 5? This means take all multiples of 5. And what does this mean? It means take all multiples of 25. So this is the set 25z, 25 times any integer, and this is the set 5 times any integer. So everything that is a multiple of 25 is also a multiple of 5. But of course, not every multiple of 5 is a multiple of 25. Did that answer your question, Alex? Yeah, okay, great. Daniel, is there a difference between the subset symbols with or without a underline? For some people, yes. For me, no. So, yeah. I use this and this. If I want to be very specific, so if I want to say that they're actually different, I'll write that. Otherwise, there's no difference between this symbol and this symbol. I don't know why I use one and not the other. Depender, I still haven't answered your question. Can you unmute yourself and ask your question?
Yeah, sure. So for the extension of ideals, the example of integers.
Uh-huh.
So the only reason why I was saying about prime elements was because if you have 25, you'll generate by 25, you can write 25 with prime factorized 25, and that's how you choose the next ideal. Okay.
Yeah, but you could choose 25 forever.
Okay.
Yeah, you don't have to make it smaller and smaller. What this is saying is there does not exist an infinite chain where you keep choosing more and more and more things. So here's a ring that's not Noetherian, okay? Let's see a ring that's not Noetherian, because these things, as I think I said last time, is just wild. Take z to the n. What in the world does that mean? That means I have a number n1 and a number n2 and a number n3, and I have a number for every natural number. I have an integer. Each of these is an integer. Okay, so think about so here's an element in here. An element in here is 3, 1, 4, 1, 5, 9, and so on. Okay, so that's an infinite sequence of whole numbers. Integers, doesn't have to be positive, could be negative, could be 0. Okay, in this ring, I can take the ideal generated by, so in here, I have, in this ring, I have the ideal generated by, let's say, 1 and all zeros. So that's a copy of z in the first factor. So it's generated by, let's see, let me write a typical element in here as a bracket, just to kind of distinguish between parentheses, which mean generate by, and bracket will be an element. So the ideal generated by the element 1 and all zeros is one ideal. Now, anything that has 1 and all zeros, any multiple of this is also a multiple. In other words, this is just z in the first factor, but that is contained inside things generated by z in the first factor and z in the second factor. The elements 1, 0, and the element 0, 1, and all zeros. So this means I can take any multiple of anything in the first factor and any multiple of anything in the second factor. By the way, what's the ring operation? How do I add two things or multiply by two things? I just multiply component by component, add component by component. Yep, element-wise, addition, multiplication. So this is multiply anything by by this, that'll only get me something in the first factor. Multiply by this, anything by this, that gets me whatever I want in the second factor, and I can add them. So I get anything in the first two factors. So that's ideal 2. This is I2. And of course I can make an I3 and an I4, and this never stops because I have infinitely many. It's like an infinite dimensional ring. Okay, so this is not a Noetherian ring. You have to get to pretty weird rings before they're, well, no, they don't have to be anywhere near that bizarre, because the ring z adjoint root minus 5 is not Noetherian. So let me make that a challenge exercise. Challenge exercise. Let's think about this. Exercise. Demonstrate that z adjoin root minus 5 is not Noetherian. I haven't thought about this at all. So find a infinite sequence of ideals. So let me make it a question. Question: is there an infinite sequence of ideals? Strictly increasing sequence of ideals. Okay, Kevin, I'm still kind of lost. What does z to the n mean in this case? N is the natural numbers. Whoops. N is the natural numbers. So in other words, I just have an infinite sequence of natural numbers. So that's my ring. Sorry, an infinite sequence of integers. Doesn't have to be positive. I need to know, to make it a ring, I have to know how to add, subtract, and multiply. How do I add? Component by component. Can I subtract? Does everything have something that you can do to, does every element have an additive inverse? Yes, just component by component, negate everybody. Is there a multiplicative identity? Well, if you're multiplying component by component, then the element 1, 1, 1, 1, 1, 1, 1, 1 doesn't change anybody. And in general, how do I multiply two things? I just multiply component by component. So that's my ring with unity, a nice ring. And the question is it Noetherian? So the point is not Noetherian. The point is not Noetherian, because I have this infinite increasing chain of ideals. It does not stabilize after finite time. This says that at some point it has to just be the same thing. Either it's all 25s the whole way down, or it's budget 25s and then 5s and then 5s the whole way down, or it's 25s then 5s then 1s. Once you hit 1s, that's it. You're done. Okay. So far so good? So let's see why being a principal ideal domain implies that you're Noetherian. So let's recall the proof. Recall the proof that being a principal ideal domain implies that you're Noetherian. Okay, so let R be a principal ideal domain, and let I1 contained in I2 contained in I3 and so on be an increasing chain of ideals. Increasing, they call them chain, it's just a sequence. The word chain doesn't have any mathematical meaning here. Chain of ideals. Okay? So in general, the union of ideals is not an ideal, but if you have an increase, so this was an exercise last time. I don't know if you guys did it. Did anyone do this exercise? Can I get a thumbs up if you did this exercise? That when you have ideals that are nested like this, the union over nested ideals, the point is these ideals are all nested inside each other, is an ideal. Okay, Yukong has a thumbs up. Dependro has a thumbs up. Karen, okay, so okay, great. A bunch of people did this exercise. So so it's very simple. If you have two, how do you check that it's an ideal? You need to know that the sum and difference of two things in here is in here, and that the product of anything by any element of R is in here. And you just check that because if you have an element that's in the union, well, it's in some element. In order to be in the union, it has to be in one of the ideals. And then since they're nested, you see that this makes an ideal. Just to see that this doesn't always have to be the case for non-nested ideals. So a non-example. What is the union of the ideal generated by 2, just in the integers, union the ideal generated by 3? Well, it would be nice if it were 6. That's a really good guess, Sarah. So if we take the product of the ideals, we would get 6. But the union means take all multiples of 2, anybody that's a multiple of 2, or a multiple of 3. That's another good guess. Stephanie's guess is this equal to all of R, which is Z, or is it maybe equal to all multiples of 6? Right, 7 isn't in there. 7 isn't in there because so the element 7 is not in here because 7 is not either a multiple of 2 or a multiple of 3. I'm not saying, right, and 5 isn't in there either. Yeah, it is what it is. It's all multiples of 2 union all multiples of 3. And 5 is not in here, and 5, so 2 is in this, let's call this set S. 2 is in S, and 3 is in S, because 2 is a multiple of 2, and 3 is a multiple of 3. But their sum, 2 plus 5, is 5. 2 plus 3 is 5. And 2 plus 3 is not in S. So S is already not an ideal. It's not closed under addition. It's just multiples of 2 plus union multiples of 3, and 2 plus 3 is not a multiple of 2 nor a multiple of 3. Okay, so that was just a little aside that in general unions of ideals are not ideals, but if they're nested, these ideals are all nested inside each other. They're growing. I1, then I2, I3, and so on is growing. So then that is an ideal. Should we do this exercise? Do you guys want to think about it, or should we do it all together? You want to type yes or no into the chat? Yes, if you want to see how to prove this. Do it all together. Okay, so let's do it. Let's do this exercise. Okay, so exercise solution. So let R and S. So let's call this big ideal. Sorry, are we back? Okay, let's call this big ideal I. I is this big ideal. Let R and S be elements of I. Okay? Well, what does it mean that R is in I? That means R is in I means there exists some J, let's call it J1, so that R is in IJ1. If you're in the union of all these things, then you're in one component. You're in some component. And similarly, there exists some J2 so that S is also in IJ2. This was J1. Now, one of these is bigger. Let J be the max of J1 and J2. The larger you are, the ideals are nested, so the larger you are, the more stuff you have. In other words, let's draw a little picture. So here again is I1, I2, I3, and so on. Maybe R is here and S is here. They have to be somewhere in the union. So if R is here and S is here, then J, so let's say this is J1 equals 2 and J2 equals 3. Can you guys see? Can you guys see this? Yep, it's not too small. Then R and S are both in I sub j. But inside I sub j is an ideal, so you're allowed to add and subtract. This is an ideal, so R plus S and R minus S are in this ideal. But that means they're in the union over all ideals. So that's how you see that the sum or difference of two elements in this massive union is also in the massive union. Kevin, you want to say something? You can unmute yourself if it's faster. Or just type, that's okay. You just thought of something. Could a particular Noetherian ring have multiple chains of ideals? I don't know if that makes sense. Like 60 is contained inside 10 inside 5, or 60 contained inside 4 inside. Yeah. There's lots of different. Yeah, there's lots of different ways of making chains. The thing about there's lots of different ways of making chains. The thing about being Noetherian is anytime you make a chain, that chain has to stop. That's the claim. Anytime you make a chain, that chain has to stop, and after a certain point, you're not increasing anymore. You're just going over the same region every single time. Okay? So yes, you can have lots of different kinds of chains going in different directions, but for any one chain, that chain cannot increase forever. Okay, so we have our principal ideal, R. We've taken some increasing chain, and the thing that we were trying to prove is that the chain can't go on forever. Now, what we just... So we showed one bit of the exercise. We showed that addition, that the union of these nested ideals respects addition. Why does it respect multiplication by elements of the ring? Let me leave that to you. It's the same argument. If you're in the union of the ideals, then you're in some component, and you can multiply. Well, I just did it for you, and you can multiply in that component, and then you're still in the union. Okay, so maybe I said that a little quickly, but I'll let you think about this. Let's call this an exercise, since I guess not everybody did it. Exercise 1. Okay? So I is itself an ideal. So this I, which is the union over all of these ij's, is an ideal. And R is a principal ideal domain. What does that mean? Every single ideal is principal. So I is generated by some element, D. So why is not any ring Noetherian? Well, because if it's not a principal ideal domain, then you could have this ideal. So in the case of this thing, we have this infinite chain. Well, what is the infinite chain? The infinite chain fills out all of z to the n. It fills out the whole ring. But it takes infinitely long to get there. Does that make sense, Karen? I figured out how to phrase my question. Karen, so your question was, why isn't every ring Noetherian? Well, this ring is not a principal ideal domain. So what you understand, the Noetherian ring is the end result of nested ideals. Well, no, it's that the nested ideals can't continue being nested forever. That's the thing that we haven't proved yet, that the nested ideals can't continue being nested forever and ever and ever. But the property itself makes it that Noetherian seems to lie in the sequence of nested rings, not the final PID itself. It's not, so it's not that this ideal is called Noetherian. It's not called Noetherian if it's a union of ideals. It's called Noetherian if it has this weird property that whenever you have this nested chain of ideals, that chain can't continue growing forever. Okay? So we haven't proved yet that this chain can't continue growing forever. For all we know, this, in the case of our principal ideal domain, for all we know, when we start making ideals, we can just keep making bigger and bigger circles. And nothing's stopping me from making bigger and bigger regions. So Noetherian is the fact that, no, you can't continue this forever. Eventually, you're just drawing the same region over and over again. So that's what I have to argue for you. I haven't done it yet. Okay? So this is, so if we take the union over all these ideals, we get an ideal. That was this exercise. And that ideal is generated by somebody, since every ideal is generated by a single element, since R is a principal ideal domain. That was our assumption. So we're very heavily using that R is a principal ideal domain to get the fact that this is generated by a single element. Does that make sense? Okay, but that single element lives somewhere. But D is an element of I. I is a union over all these ideals. So it lives somewhere. Where? Where does it live? Well, in some ij. So there exists a j, let's call it capital N, such that D is in I capital N. Does everybody see that? But D is in I capital N. That means the ideal generated by D is contained in I capital N. But the ideal generated by D is everything. So the entire union is contained in I capital N. So when we add all of the ideals that we add after we add the nth one, we don't add anything new. So all of the ideals after in are just the same as in itself, because they're nested. They can't get smaller, and they can't get bigger. So let me write that out. So all the ideals in after I big N, so all the future ideals after I big N, well, they contain in, but they also can't contain anything not in in. Does that make sense? But they can't add anything new. They can't add any new elements to the union over all future ideals, because that union over all ideals is just in itself. Okay. Does that kind of make sense? A little bit? All right. So this is the new property, and I don't want to belabor it too much, but it's an important one for you to at least have been exposed to. We're not going to use it. My goal was not to do very abstract things, but I don't know if it was your questions or just I was in the mood. Before we went online, I was in the mood to do a little bit more abstract things than what we had been doing. Now I want to get very, very concrete, because this stuff is really hard to do without people sitting there, looking over your shoulder and holding your hand through it. So let's very quickly finish this story, just to say we finished it, and move on, because there is something I want to do with it. So the end of the story is that, last step is that Noetherian implies unique factorization. Okay, that's the last thing that I want to do, which will imply that the Eisenstein integers have unique factorization. Because the Eisenstein integers have a division algorithm, and hence are a principal ideal domain, and hence are a Noetherian domain. Okay? So the first step to showing this is to say, so step one, let's call this a lemma. Lemma. If R is Noetherian, then any element, any non-unit, well, let me write it first and then any element R in R is a product of irreducibles. Remember what it means to be irreducible? What does it mean to be irreducible? If S divides R, then S is either a unit or an associate. Yeah, all factorizations involve a unit. So either they differ by a unit or S itself is a unit. Okay? So so the question is, why is every element a product of irreducibles? So in the case of integers, it was like, well, if it's not irreducible, break it down and then break it down and break it down. How do you know that breaking down process eventually stops? Right, it's like the first part of the fundamental theorem of arithmetic, but what would make an infinite sequence stop? Shane is writing something. Yes, Noetherian, exactly. That's the beauty of Noetherian. Noetherian makes an infinite process stop. Okay? So let's prove this lemma. Right, so irreducibles, it could be an empty product of irreducibles, and I guess 0 is a product of 0 times irreducibles. So maybe you want to take out the 0 element, or maybe you want to take out the units out of this lemma, but actually it's still correct as stated, that every element is a product of irreducibles. So let's prove this. So if R is not irreducible, if it's itself not irreducible, then there exists an R1 dividing R, where R1 is not a unit and R1 is not, the ideal generated by R1 is not the ideal generated by R. Okay? So if R is not irreducible, then there is some factor. But that factor doesn't have to be irreducible. All we know is that there's some factor. Now, if R1, so the first thing we want to prove is that it at least has one irreducible factor. So this is, I should have said, what we're going for. Claim is that there exists an irreducible. There exists some, what should I call irreducibles instead of R's? I don't want to use I. Somebody give me a letter. A letter for irreducibles. L. Great. Thanks, Sheik. Some L dividing R, where L is irreducible. Okay, so my first claim is that it has an irreducible divisor. I don't even know that. I don't know that a single irreducible element divides R. So if it's not irreducible, then there's some element which is not a unit and which is not all of R that divides R1. And if R1 is itself not irreducible, then there exists R2 that divides R1. And R2 is not a unit. And the ideal generated by R2. Now, let's think about this. R1 divides R. So which way does the equality go here, inequality go? Is everything that's a multiple of R1 automatically a multiple of R, or the other way around? Is this a less than sign or a greater than sign? You guys want to write that in the chat? So less than, that means that anything that's a multiple of R1 is automatically a multiple of R. So think about R is 6 and R1 is 2. Anything that's a multiple of 2 is automatically a multiple of 6. Yeah, so it goes the other way around. It goes the other way around. Anything that's a multiple of 6 is automatically a multiple of 2. This is the set of multiples of 6. This is the set of multiples of 2. Okay, so if R1 is not irreducible, then there's some other element which increases R1. And so on. And that gives us this chain of ideals. R is greater than and not equal to R1, is greater than and not equal to R2, is greater than and not equal to R3. Can that continue forever? You can each write a yes, a Y, or an N in the chat. Just humor me. Write a Y or an S and Y or an N in the chat, please. So I know. Okay, we're here. Right? You guys see that? This can't go on forever. Shane, why not? You just told us why not. Kevin, you're saying yes, it can go on forever. Are you just messing with me? Oh wait. Right, Noetherian. Right, but R is Noetherian. So can't go on forever. What does that mean? When does it stop? Yeah, at what point should we stop? Remember right at the very beginning I said if R1 is not irreducible, if I haven't found an irreducible, then I keep going. If R1 is not irreducible, then I can find an R2. And if R2 is not irreducible, then I can find an R3. And if R3 is not irreducible, then I can find an R4. So at which point would it stop? It would stop. It has to stop. Must stop. Must stop. And stops when Rj, when one of these divisors is purple. No, irreducible. Sorry, I spend a lot of time with my kids these days, so that's a dad joke. It must stop, and it stops when Rj is irreducible. Okay? Does that make sense? Well, what does that mean? Rj is a divisor. Rj divides Rj minus 1, which divides Rj minus 2, which divides R. And so we have found an irreducible divisor of R. So that means there exists, what do we call it? L dividing R, which is irreducible. L is irreducible. So what have we learned? Every element which is not itself irreducible has an irreducible factor. Okay, so that means we can pull out an irreducible factor. So step 2, this was claim 1. So now claim 2 is the full proof of the lemma, which is every element is a product of irreducibles. So now I want to be able to write R as a product of irreducibles times units. I mean, irreducibles, a product of units and irreducibles. Okay? So, y is r equal to a unit times L1 through Ln. These are all irreducibles. And this is a unit. Well, what we just showed is that R has a irreducible divisor. We just showed that there exists an L1 dividing R with L1 irreducible. Right? What does it mean to divide? So there exists S1 such that R is equal to L1 times S1. Right? R has an irreducible divisor. If R itself is not irreducible, then it's L1, which is irreducible, times somebody. Exactly. Repeat the process on S1. So if S1 is not irreducible, by the previous lemma, there exists an L2 dividing S1 that is irreducible. L2 is irreducible. Okay? And S2 is equal to L2 times some other element, S3. And so now we get this chain. The ideal generated by R is contained inside, well, S1 is its divisor, and S2 is a divisor of S1, and S3 is a divisor of S2, and these are not equal because they're genuinely getting, well, I'd like to say smaller if you want to think about it in terms of norm, but they're just contained. Anything that's a multiple of S2 is automatically a multiple of S3. But actually there's an irreducible factor in between, so this is a chain which is strictly increasing. Yes, Noetherian implies, yes, is a finite product. Yes, is a finite product of units and irreducibles. There can be infinitely many irreducibles, but the product has to be finite. Okay, so we have this chain. We have this chain. The chain must stop. Chain must stabilize. After some point, it must stop. I can't get new elements that are genuinely new. So at some point we find an irreducible element. So some S capital J is itself irreducible, and R is equal to L1 times L2 times Lj times Sj, which I can call, well, let me write it as Sj, and these are all irreducibles. All irreducibles. So in a Noetherian ring, let's review what we just did. How do I show you all of this? In a Noetherian ring, every element is a finite product of irreducibles. Okay? So we used Noetherian twice in this proof. This is kind of really, I hope you appreciate how powerful Noetherian is. The first time we got an irreducible element, a single irreducible element, so that we knew that we could pull out irreducibles. And once we knew we could pull out irreducibles, we can pull them all out one by one, and it has to stop after a finite amount of time. All right. So what that means is that the Ord function is well defined. So a corollary, well, let's see, do I want to call it a corollary or do I want to just say lemma? It's not exactly a corollary. It's a corollary of the proof technique, but it's not a direct corollary of the previous statement. So a lemma is that the Ord function has the same behavior that it had over the integers. So there exists, so given a prime P in the ring, prime in the ring, we had an exercise. Did people do the exercise that prime is equivalent to irreducible in a Noetherian, in a principal ideal domain? Okay, let me write this. Okay, before this lemma, there was an exercise. I think I did one direction for you. Let's make this exercise 2. I hope you did it. Is that in a principal ideal domain, prime if and only if irreducible. And you remember what prime is. Prime, recall, because these two things are now their own definitions. They're separate definitions. P is prime if P divides a product implies okay, thumbs up. You guys know what's coming. P divides A or P divides B. Or both. Okay? So one direction is easy. One direction is always true. If you're prime, then you're always irreducible. Is that the direction that's always true? One direction is always true, and the other direction is not always true. And I'll let you figure out which one's which. But in a principal ideal domain, they are equivalent notions. Okay. Should we go over that, or you guys are happy with that? Give me a thumbs. Give me a thumbs down if you are unhappy with that, and we should talk about it some more. Give me a thumbs up if you are happy. No one's doing anything. Is the screen frozen? Okay, there's a bunch of thumbs up. Oh, let's talk about it. Let's talk about it, Chief. Yes, Kevin. Okay, good. Let's go over it. Fine. So, if P is a prime, the question is, why is it irreducible? So let's just prove both directions. Fine, I'll do the exercise for you. So, if P is prime, so I want to prove that P is irreducible. Okay, so if P is prime and let's say R divides P. My claim, what I want, so this is what I'm given, want to show that then R is either a unit or R is associate to P. Right? So which direction, let me think for a second, which direction is the one that I always have to do this from scratch. If P is a prime and R is a divisor of P, I promised I would take a break, and here I am. We're almost at full time. Let me do this next time. I want to give you a very clean, crisp, quick derivation of this and not try to do it on the fly. So let's come back to this. Let's come back to this fact. One direction is easy, one direction takes a little bit of work, but it's not much work. Let's just take this as a given and then prove the lemma that I wanted to prove. The lemma is given a prime equivalently irreducible P in R. Where was I going with this? There is an ORD function and an element A in R. There exists an integer, a natural number, n, so that P to the n exactly divides A. i.e., in other words, P to the n does divide A, and P to the n plus 1 does not divide A. Okay, in which case, we say that the ORD of P, ORD set P of A is n. So if we have this ORD function, and it behaves the way it's supposed to behave, it behaves like a logarithm, then we're golden. Okay? Then we exactly mimic the proof of unique factorization that we had before, that we know and love. So why does this, how do we prove this lemma? So if P divides A, then A is equal to P times A1. And if P divides A1, then A1 is P times A2. And so we get this chain, dot, dot, dot. So we get a chain, A contained in A1, contained in A2, and so on. And the chain must stop. Let's see. Did I say somewhere that the ring is Noetherian? Assume R is Noetherian. That's the whole point of this argument. Assume R is Noetherian, then there is some. Then you can't divide an element can't divide a ring can't divide A infinitely much. At some point you run out, so it must stop because you're Noetherian, which means P2 wherever the place that it stops does divide A and the next one does not. Okay? Same argument. I mentioned it was a PID. Say it again. You want to unmute yourself, DePendro?
Never mind.
Oh, okay. Okay. So if I have a Noetherian ring, then if I have a prime element, then there is an ORD function. And now the proof is exactly the same as, well, there's one more thing. There's one more lemma. There's one more lemma. The proof of that is the same as the other, as the original version, which is that if R is Noetherian and P is prime, then ORD sub P of AB is ORD sub P of A plus ORD sub P of B. And this is A and B are elements of the ring and not 0. Because I can't take log of 0. Okay? And the proof is the same. Exactly the same. Do you remember what it was? Kevin, you wanted to ask something? Yes, a non-Noetherian ring can have primes. Absolutely. Yeah, but they'll have really funny behavior. Well, as we saw. We already saw in this ring, there are, I guess we didn't really talk about it. So the question was, this has both primes and irreducibles, and some primes are irreducible, but some irreducibles are not prime, and some irreducibles, for example, 1 plus root negative 5 is irreducible, are not prime. Because this divides the product of 2 times 3, but doesn't divide 2 and doesn't divide 3. Okay, Kevin? So if you remember what the proof was, all right, let me just quickly sketch what it was. So what was it? It was that, let's look at if P to the n divides A and P to the m divides B, then certainly P to the n plus m divides A times B, right? Because of what this means. since this means that a is equal to p to the n times a1, and this means that b is equal to p to the m times some b1. So a times b is p to the n plus m times a1 times b1. Okay, so p to the n plus m definitely divides a times b. If no higher power of p divides this, then a1 and p have GCD1. These two have GCD1. So if p to the n exactly divides a1 and p to the n exactly divides b, then a1, the GCD, so the ideal generated by a1 and p is the whole ring, and the ideal generated by b1 and p is also the whole ring. And so p can't divide the product, so p does not divide a1 times b1, because then it would have to divide one of them, since p does not divide a1 and p does not divide b1. And that's exactly what prime elements are. Okay, so this is the highest power. N plus m is the highest power that divides. So p to the n plus m exactly divides a times b. Okay? So far, so good? I'm basically out of time, but let me just say that was the last step to unique factorization. So now we have a theorem. Noetherian implies unique factorization. Next time we're going to do something fun. We're going to get away from this abstract stuff. I think it's hurting all of our brains to be doing all this abstract stuff over the internet. We're going to get back to very concrete things. But I just wanted to get the unique factorization in the Gaussian, in the Eisenstein integers, and thought this was a fast way to do it before we had to go online. Why does Noetherian imply unique factorization? Well, we know that any element is decomposed into irreducibles. Any element, how do I want to say this? So let's state the theorem first. Any R in R is uniquely expressed as R is equal to some unit times product over all primes, primes to some powers. This is a unit. This is a prime. This is some natural number. And that natural number is, what is that natural number? It's the ord. Ord sub p of R. Okay? So you fix some list of primes. You take inequivalent primes. So you fix some list of primes. In other words, in the integers, well, both 2 and -2 are prime. So you don't want to take both of those. Some list of primes up to equivalence, up to associate, a list of unassociated primes. Unassociate primes. So up to equivalence, up to associativity, equivalence. So you don't take 2 and -2. You don't take 3 and -3. So any primes that are inequivalent, you just fix some list of those. Then you have primes to powers. And of course, this only works for the element, for the non-zero elements. And that's unique factorization exactly for the same reason as before. You take ord of both sides. So proof, fix some prime q, and take ord sub q of both sides. And then the proof is exactly as before. All right. We're going to move on Tuesday away from this abstract stuff and back to some fun number theory that's very explicit and you can get your hands dirty with.